Hello students, welcome to Sources classes. Today we will be talking about complementary functions. So in our previous video on linear differential equation, we explained it to you that the general form of a solution of a linear differential equation is of the type y is equal to complementary function plus particular integral. So this is the format. So today we'll be talking about the complementary function. Now let me write down. Let us understand the general form of a linear differential equation with constant coefficients. So it will be basically of the format dn by dx of n into y plus k1 into dn minus 1 into dn minus 1 by dx minus x to the power n minus 1 into y plus k2 into dn minus 2 by dx to the power n minus 2 into y, and this will go on up till plus k1 kn of y, and that will be equal to capital X. That will be equal to capital X, where k1 k2 k3 up till kn are all constants and capital X is a function of x. This is a linear differential equation with constant coefficients. If we did not have this restriction, then we could have written k1 k2 up till kn are all, including capital X, are all functions of x. But here we have k1 k2 k3 and kn are all constants. So this is the general form of a linear differential equation with constant coefficients. So if we have an equation of the type dn by dx to the power n y plus k1 into dn minus 1 dn minus 1 by d to the dx to the power n minus 1 y plus k2 into dn minus 2 dx to the power n minus 2 into y up till kn of y is equal to 0. So basically capital X became 0 over here, where k1 k2 are all constants, where let me write it down again, where k1 k2 k3 up till kn are all constants, then this can be written down in the format dn of y plus k1 into dn minus 1 into y plus k2 into d to the power n minus 2 into y, and up till kny is equal to 0. So if we take y common over here, then this can be written down as the format dn plus k1 into d to the power n minus 1 plus k2 into d to the power n minus 2 up till kn into y is equal to 0, which can be further simplified as f of d into y is equal to 0, where f of d is equal to d to the power n plus k1 into d to the power n minus 1 plus k2 into d to the power n minus 2 up till kn. Now this entire term dn plus k1 into d to the power n minus 1 plus k2 into d to the power n minus 2 up till kn, this is nothing but the auxiliary equation, which is denoted in short by AE. So this is the auxiliary equation. Now if roots of this auxiliary equation are m1, m2, m3 up till mn, then there are various cases for which then using these roots we can find out the complementary function. Using these roots we can find out the complementary function. Let me denote the various cases for you. So thing is that using the roots of the auxiliary equation, we can now find the complementary function. So this is now possible. So the roots are basically, the roots as we already mentioned are m1, m2, m3 up till m of n. So there are various cases that we need to consider now. There will be a case 1. So let us talk about case 1. So case 1 are that roots of the auxiliary equation are real and distinct. So basically, that is, we can write down that m1 is not equal to m2, it is not equal to m3, and so on up till mn. So therefore the complementary equation will be of the format, therefore y will be equal to c1 into e to the power m1x plus c2 into e to the power m2x, and this will go on up till cn into e to the power mn of x. So this is the complementary function format in such a case. Now let us go on to the next case, which is case 2. So in case 2, here we have seen that some roots of the auxiliary equation are real and some are equal. So that means that m1 can be equal to m2, but they are not equal to m3. That is, this basically means like this. So in that case, we'll have y of the format c1 plus c2x into e to the power m1x plus c3 into e to the power m3x, and so on. So this is another structure that we'll get if we have some roots of the auxiliary equation are equal. Now let us move on to the next case, which is case 4. Not case 4, I have wrongly said the number, it will be case 3. So case 3 will be that some roots of the auxiliary equation are complex. So basically then roots are, we can write alpha plus I beta, then we can have alpha minus I beta, then we can have the other roots, that m3 up till we can have mn. In that case, y will be of the format e to the power alpha x into capital C1 into cos of beta x plus capital C2 into sine of beta x plus c3 into e to the power m3x plus it will go on up till cn into e to the power mn x. So this will be the format of the complementary function. Now if let me where there is another thing to be considered, where capital C1 is equal to small c1 plus small c2 and capital C2 is equal to I into small c1 minus small c2. So these are things that you need to keep in mind. Now there is another thing that needs to be noted down. So note if the complex roots are equal, then we'll have a complementary function of the format where y will be equal to e to the power alpha x into small c1x plus c2 into cos of beta x plus c3x plus c4 into sine of beta x, and plus this will go on up till cn into e to the power mn of x. So this will be another format of the complementary function. So today we have talked about complementary functions in detail. Let me repeat you the cases the cases once more. So basically, if we have the auxiliary equation, and then m1, m2, m3 and mn are the roots of the auxiliary equation. Now if the roots of the auxiliary equation, let me use a separate ink so that it's more clear to you. So if we have the roots of the auxiliary equation are real and distinct, such that m1 is not equal to m2, m2 is not equal to m3, m3 is not equal to mn, in that case the complementary function y will be equal to c1 into e to the power m1x plus c2 into e to the power m2x plus cn into e to the power mnx. This is the case 1. Case 2 will be some roots of the auxiliary equation will be real and equal. Suppose m1 is equal to m2 and they are not equal to m3 and so on. In that case y will be equal to c1 plus c2x into e to the power m1x plus c3 into e to the power m3x and so on. So this will be another structure. The third structure case will be that some roots of the auxiliary equation will be complex. Suppose we have two roots which are complex, that is alpha plus I beta and alpha minus I beta. And one more thing that needs to be considered is that when one root is alpha, when we have one complex number as the root of an auxiliary equation, then its complex conjugate will be also the root of the auxiliary equation. So basically if one root is positive, so we have always complex roots in pairs. So that is to be remembered in all cases. So alpha plus I beta, then alpha minus I beta are two roots, then we have m3 and up to 11, which are all real roots. So in that case y will be equal to e to the power alpha x into capital C1 into cos of beta x plus capital C2 into sine of beta x plus small c3 into e to the power m3x, and it will go on up till small of cn into e to the power mnx, where capital C1 is equal to small c1 plus small c2 and capital C2 is equal to I into small c1 minus small c2. Now there is one more thing, that if the complex roots are equal, then what will happen? Then y will be of the format e to the power alpha x into small c1x plus c2 into cos of beta x plus small c3x plus c4 into sine beta x, and this will go on up till cn plus cn into e to the power mn of x. So this is all about complementary functions. In my next video I'll be talking about particular integrals in detail. If you have any doubts so far, then you can comment in the comment section below and we'll get back to you. Thank you very much.